showing that the unshared or unpaired electron can be delocalized over 2 carbons in this system. And if we think about this in terms of our pi electrons and how they're overlapping to make pi bonds, right? Here we have the carbon connected to that carbon, and I'm gonna try to draw it sort of flattened out. So here we have an unhybridized p orbital that overlaps sideways here and here to make this pi bond. But then if we remember what a radical is, the carbon that it's the unshared electron is on is also sp2 hybridized. So radicals, the carbons bearing the radical are also planar, right? So therefore, if you have another sp2 hybrid carbon here with an unhybridized p orbital bearing that unshared electron pair, then what's to say that that unhybridized p orbital can't also overlap sideways with the one next door to it? So therefore, how this radical feels is like, you know, I don't have to limit myself to being here, because through overlap, I can also sneak over to this position. And therefore, at any given moment, if we understand what resonance means, it means that there is a degree to which that unshared electron is localized in both this position and that position. Right? It's not one or the other. It's localized to some degree in both places. So another way that Brooke was trying to describe this system, when I asked, you know, what would make it more stable, is that we can also say that this unshared electron, being one carbon away from a pi system, we can refer to that as being conjugated with the pi system. So anything that's one carbon away from a pi bond can be delocalized with that pi bond through resonance, right? And essentially what that is telling us, so resonance is one way of one model for illustrating this, but what's embedded in the meaning of that is that you have all of these carbons that are all sp2 hybridized, meaning all of them are in the same plane, all bearing unhybridized p orbitals that can overlap continually to have a completely delocalized pi electron system. And so the molecule has an option for where it can localize some of this unshared electrons density. Right? The only place where what resonance helps us to refine for this theory is that we never see evidence of that unshared electron being on the middle carbon. You know, somehow the delocalization allows it to show evidence of itself on the 2 carbons at the greatest extremes here. But again, that's how you would be able to draw it through resonance to figure that out. Much to the chagrin of some of you, much to the regret of some of you. in relative terms, if you look at tables of homolytic bond dissociation energies, you'll see that the allyl radical is more stable than a benzyl radical. Which is more stable than a tertiary, secondary, primary methyl. So when we get into chapter 16, we might have a better appreciation for why the benzyl radical or benzylic radical is not as stable as the allyl or allylic radical, even though it seems like there's more ways to delocalize that through resonance. But this ability to delocalize through resonance is going to give us some options whenever you have systems where you can form radicals or other species that are, as we would say, conjugated. So for example, if I were to take that compound, we'd want to ask ourselves, how many products can you form potentially? So, yes, Alex.
Is the radical just as likely to be kind of above the plane as below the plane of the molecule? Like, is it
Yeah,
equally
there's
shared
no,
on both planes?
because the carbon bearing the radical is flat, there's no distinction of above or below the plane. So once you form a radical, it would scramble your stereochemistry. All right, so the first thing we'd want to say is, okay, how many different allyl radicals could be formed from this? So if this goes through a radical, we might have a radical that puts the unshared electron in that position. But we might also have a radical that puts the unshared electron in that position. So those are two allyl radicals that we could form as intermediates in this reaction. But those two allyl radicals are now conjugated with the pi bond.